Hey there and welcome. Today, we are going to dive into one of the most powerful ideas in all of science. Seriously, it's a concept so simple, yet it unlocks, well, pretty much everything. From how a jet engine roars to life, all the way to the fate of a black hole. And it all starts with learning how to draw a line. So let's just jump right in with a big question. Where does energy actually go when something heats up or cools down? I mean, really, where does it go? To even begin to answer this, science uses this brilliant little trick. It's all about precisely defining what we're looking at, we call that the system, and then separating it from literally everything else, which we call the surroundings. So here's the plan. We'll start with the core idea of systems and surroundings. Then we'll check out the different personalities a boundary can have. After that, we'll classify the three fundamental types of systems, learn how to track the currency of energy with the first law, see how that rule changes for open systems, and then we'll wrap it all up with the big takeaway. Okay, let's get started. All right, Section 1, the core idea. This is really all about how physicists can make sense of the entire universe just by drawing a line. It really boils down to this incredibly powerful distinction. On one side, we define our system. Think of this as the star of our show, the specific piece of the universe we want to study. And it can be anything. And on the other side, the surroundings. And that is, not kidding, literally everything else. By making this clean break, we can carefully, meticulously track every single thing that goes in and everything that comes out. Now, that line we draw between the system and the surroundings, that's called the boundary. But look, this isn't just some passive divider. It is the rule book. It can be a real physical surface, like the aluminum wall of a soda can, or it can be completely imaginary, like just drawing a box in your mind around a parcel of air. Either way, this boundary is what controls all the action. And this brings us to a really common misconception we got to clear up right away. A system does not have to be a solid object. Not at all. As you can see here, it could be a single living cell, a puff of air, the guts of a jet engine, or even a totally empty region of space. The key is, the choice of what the system is completely up to us. Okay, so if the boundary is the rulebook, what kind of rules can it have? Well, that brings us right to Section 2, boundary personalities. These are the specific rules that govern the flow of both energy and matter. This table here lays out the three key questions you always ask about a boundary. First, can heat get through? If yes, we give it a fancy name, diathermal. Just think of a simple metal pot. If no, we call it adiabatic. That's your perfect insulator, like an ideal thermos. Second question, can matter cross it? If stuff can get through, it's permeable, like a cell membrane. If not, it's impermeable, like that sealed can again. And finally, can the boundary itself move? If it can, it's movable. Picture a piston in an engine. If not, it's rigid. Honestly, getting these terms down is like learning the basic grammar of thermodynamics. Now here's where things get really, really cool. By just combining these few boundary properties, we can actually classify every single process in the universe into one of just three categories. That's Section 3, the three systems. It's like a universal filing system for reality itself. And it's so beautifully simple. First up, you've got an open system. This one exchanges both energy and matter with its surroundings. Next, a closed system. It only exchanges energy, not matter. And finally, the most extreme case, an isolated system. It exchanges absolutely nothing. No energy, no matter. Zip. Let's make this feel a little more real. An open system, that's just like a living cell, constantly taking in food and getting rid of waste. A closed system is that sealed can of soda we keep talking about. Sure, heat can get in and warm it up, but the soda itself isn't going anywhere. In an isolated system, well, a perfect thermos is the ideal we're shooting for, but in the real world, it's just an idea. Which, of course, leads to this pretty profound thought. If a perfect thermos is just an approximation, what's a truly isolated system? The answer is the entire universe. I mean, think about it. By definition, there are no surroundings outside the universe for it to exchange anything with. It is the ultimate and the only perfectly isolated system we know. So now that we have our filing system set up, let's move on to Section 4, the currency of energy. How do we actually keep track of what's flowing across that boundary? This is where the famous first law of thermodynamics makes its entrance. First things first, we need to define the energy that's already inside the system. We call this internal energy, and we use the letter U for it. You can think of it as the grand total of all the microscopic energies going on in there. Molecules zipping around, the energy locked up in chemical bonds, all of it. So how can we change that internal energy? Well, it turns out there are only two ways for energy to cross the boundary. It can cross as heat, which we call Q. That's just energy moving because of a temperature difference. Or it can cross as work, which we call W. That's energy transferred by some kind of organized force, like a piston pushing on a gas. And this all brings us to one of the most beautiful and powerful equations in all of physics, the first law of thermodynamics. Delta U equals Q plus W. It's such a simple statement, but the implications are huge. It means the change in a system's internal energy is exactly accounted for by the heat you add to it, plus the work you do on it. It's really just a perfect energy accounting system. Energy isn't created or destroyed, it's just moved around. If you add 10 joules of heat and you do 5 joules of work on the system, its internal energy must go up by exactly 15 joules. End of story. It's conservation of energy, plain and simple. But, that law works perfectly for closed systems. But what about open ones? That takes us to Section 5, the open system rule. What happens when matter itself is on the move, crossing that boundary? Right. When a chunk of matter flows across a boundary, it brings its own internal energy, U, along for the ride. But that's not all. You also have to do some work just to shove it into the system against whatever pressure is already there. We call that extra bit flow work. So we bundle all of that together into a super useful new quantity called enthalpy, or H. And I love this description. It's the total energy ticket for that piece of matter. The equation for it is H equals U plus PV. So enthalpy is the sum of the internal energy, U, plus that flow work, which is just the pressure, P, times the volume, V. Believe me, this concept is absolutely essential for any engineer analyzing anything with fluid flow, from power plants to rocket engines. Okay, let's pull all of this together now. In Section 6, the big takeaway. Why is this seemingly simple idea, just drawing a line, one of the most powerful concepts in all of science? It's because of this one deep insight. The physics of any situation, the answer you get, the understanding you walk away with, it depends entirely on where you, the scientist, decide to draw the line. Choosing your system, it's not just the first step. It is the very act that defines the problem itself. And this right here, this is the ultimate payoff. The sheer power of this one framework is just astounding. By just defining a system and carefully tracking what crosses its boundary, we can analyze the engineering of a jet engine, we can understand the incredibly complex biology of a living cell, and we can even probe the thermodynamics of a black hole's event horizon. It's the exact same fundamental toolkit applied everywhere. So I'll leave you with this thought. This simple act of drawing a line, it's not just for physicists. It's a tool for thinking. It lets us bring order to any complex problem and find real clarity. So the only question left is, what boundary will you draw to understand your world?